All right, here we are for AP Physics Potential Energy, problem 2. A block slides down a curved frictionless track and then goes up this incline. There's friction, though, between the block and the incline. So it's not going to make it back up to its original height because it's losing some energy here because of that friction doing work against the system, taking energy out. Energy is getting converted into thermal energy as it rubs. They tell you the coefficient of friction here is mu k. They want you to use an energy technique to show the maximum height up the incline reached by the block. So that vertical height here, Y max, is going to be given by this expression. So what I'm going to do is I'm going to get ready to do an energy calculation. Again, we see changes in height. You should start thinking I'm going to use an energy calculation, especially when the path is some weird curved path. Potential energy is awesome to use because you don't have to worry about the path it takes, just the starting and final heights. So we're trying to solve for height. So we're going to do a calculation from here to here, right? From where it starts to where it ends. Okay, big energy calculation for that whole process. So here we go. Okay, I'm going to work this out on a separate paper. So I'm going to go ahead and sketch in. I'm going to go ahead and draw this whole sketch again. I know. It seems silly when I got it right there, but here I go. Again, on an AP exam, you probably wouldn't have to do this. They would give you a nice sketch to work with, but what are you going to do? All right, so we're going to start off up here. We are trying to find. Okay, so there is a mistake on this diagram. Holy cow. You see that H? That's the starting height of the block. I'm sorry, that got left off somehow. Dang it. Okay, so that was given here. I'm sorry, in case you were wondering what that H variable meant, right? Okay, that's the starting height. Okay, it's H. Sorry, yeah, you absolutely need that to solve, for heaven's sakes. Right, so here we go. Whew. Whoops. All right. So taking a look at this. I know at this point there's someone out there who's like, oh, yeah, I know. Me too. All right. So here we go. We're starting at height H. And at the end, we're going to end up over here. Again, we are always choosing a starting and ending locations for our problem. All right, and in this, we're going to do an energy calculation. We got a start point and an end point. We are going to go from here to here, right? Okay. All right, here we go. We're going to set up the big work energy theorem. Sigma W is delta K plus delta. Whoops, I don't have any deltas yet. You know I'm gonna. It's no surprise. No one's gonna be surprised when I tell you, hey, let's make our system be both the block and the Earth. Let me just jump right ahead to that. That means I'm going to have a delta UG. Okay. Hey, sigma W, I put a work term in for every force. What forces are acting the block as we go from here to here? You would agree there's gravitational, there's normal, and there's friction. Those are the three forces. There's not going to be a work by gravity because I included the Earth in the system, and so that gravitational force technically wouldn't show up. But I am going to have normal force and friction force. All right. My initial velocity here is 0. And when I'm at the highest point, my ending velocity is going to be 0. So those two kinetic energy terms are the same size, right? They're both 0, 0, 0, 0 minus 0, 0. That's all going to go away. Delta UG, so I'll have my UG final minus UG initial, and that's it. Okay, that's what the line's going to look like. You say, oh, no, wait. This normal force, is it going to do work? And you're going to say, no, it's not going to do work because the normal force is perpendicular to the motion at all times in this problem. So I really am just going to have these three terms. Work by friction is going to be the difference between the potential energy terms, right? Okay, I'm going to lose some gravitational potential energy. These aren't going to balance out because I'm going to be missing this energy that leaves the system because of friction. All right. Hey, the work done by friction is put in our friction equation. That'll be integral of F dot dx, right? That friction force dot dx. I'll put in all the rest of these terms too. UG final will be mg times the final height. Well, the final height, that's what we're calling Y max, minus mg times the initial height is what we're calling h there. Again, I apologize, that was not on the diagram. It got left off by accident. Sorry about that. All right. Yep. Okay, now on this side, hey, this integral form. You say, what's the angle between friction and the motion? We'll be moving along the ramp like that, and friction will be going against the motion. That's going to be a cosine 180. That entire time the friction force is acting, it's only acting while we're going up the ramp. That's going to be 180. And the friction force, it's going to be a constant force, that kinetic friction. So constant, constant. I can just move those out of the integral. It'll just be the integral dx. That's just delta x. This is just going to be friction times cosine 180 is minus 1 times, delta x. All right? And at this point, things are looking good. You say, now how big? We weren't given the friction force, but I can see I need to get theta and I need to get a mu in my answer somehow. How am I going to get that? We're going to rewrite the friction force as mu n. Okay, now there's the mu we're looking for, right? Minus 1, just made a minus there, delta x. All right. Things are looking better. I don't know why I'm just going to work on this left side. Now that normal force, how big is the normal force going to be? Let's do a quick force diagram for that block as that friction force is acting as it's sliding up the ramp. We're going to have our gravitational force, mg, and a normal force sticking straight out of the surface, and a friction force acting along here. I would split that gravitational force into components going perpendicular and parallel. You say, hey, that angle of the ramp, that's this upper angle, that's the theta. And so this side is going to be mg cosine theta, mg sine theta. Okay, mg cosine theta, that's balancing out the normal force because we're not accelerating this axis. And so the n, I could substitute for the normal force mg cosine theta. And now something wonderful is going to happen. Okay, or almost. Now what about this delta x? That's the distance I go along the ramp. I'm going to do a little geometry here, right? Look, that height there, there's a little right triangle, all right? Delta x is the length along the ramp that I slide there. And you say, look, those are two sides of a right triangle with an angle theta there. This is the opposite side. That's the hypotenuse. Opposite of hypotenuse is sine of theta. So wouldn't you agree, doing a little geometry there, I'm going to write it over here, jam it in here, whatever. Anyway, you would agree that the sine of theta is the opposite of the hypotenuse. So it would be y max over delta x. So rearranging this, delta x would be y max over sine theta. I'm going to substitute that in here for delta x, okay? So that's the substitution I'm going to do. So that'll be y max over sine theta. All right. I'm just going to copy this line down again because I can't help myself. All right. We are trying to solve for y max, right? So I'm going to group my y max terms together. Let me add this term to the other side. Let me move the mgh over here. mgh is going to be mg y max, right? And I'm going to add this term over plus mu mg cosine theta over sine theta times y max. All right. This is where someone says, if they haven't said so yet, oh my gosh, Mr. C, I can see that every term has an m and a g in it. Right? And cosine over sine, I know sine over cosine is tangent. Cosine over sine, that's cotangent. And things are looking real good now. Right? You're like, okay, let's factor y max out of the side. Y max times 1 plus mu cotangent theta. And finally, let's move this underneath that side, and we have our expression that y max is h over 1 plus mu cotangent theta, which is what they wanted us to show. All right, ta-da! And that's that problem. Again, I apologize that h got left out, so you didn't know what that variable stood for. My bad, sorry. But that's the problem. So yeah. Okay, nice problem. Again, it's okay. We can have this work term by friction. We just realize it's okay that friction is not acting through the whole motion. It's only acting along delta x there. That's okay. That's why we only use the distance delta x when we calculate the work done by friction force there. Okay, that is problem 2.